Okay, we're ready now to start the final tool that you need to do circuit analysis. And circuit analysis is going to be the main focus of our next class. But anyway, the rules that I'm talking about are Kirchhoff's circuit rules or circuit laws. And a guy by the name of Kirchoff many years ago did some circuit analysis and came up with a couple really simple rules that allow us to analyze the current and the voltage in different types of circuits. And the beauty of it is they apply to any type of circuit, be it a series circuit, a parallel circuit, or maybe even what we call a combination circuit. In other words, has some series, some parallel, a bit of both. So let's take a look at how these work. So first of all, let's take a look at the difference between a series circuit and a parallel circuit. And you should know the difference between those already. In a series circuit, there's only one single path for current. In other words, all the electrons that leave the battery right here have to go all the way around the circuit and go through every resistor in the circuit. There's only one path. That's what we call a series circuit. But a parallel circuit has more than one path. In other words, once it gets here, the current splits. Some goes this way, some goes this way. We call this point right here a junction point or a node. Okay, and they become very important when we start talking about current in particular, because the current splits when we have a junction like that. Splits off. Some goes one way, some goes the other. Okay, and this is what happens when you have two things parallel. In other words, usually drawn side by side. So that's the difference in a series and a parallel. So let's look at the current law first. So the current law says this, that the total current entering a junction point of a circuit must equal the total current leaving the junction point. So at this point right here, for example, if current 1 comes in, it splits two ways. Some goes 2, some goes to 3. So in other words, I1 equals I2 plus I3 for this particular one. But the current could be flowing in the other direction as well. It could be coming into the junction point two ways, in other words, I2 and I3, combining into one current, which we call I2. So I2 plus I3 also equals I1. So it works both ways, in other words. Okay, that's the thing you need to remember. It can go either way. Doesn't matter. So how does that work? Well, in a series circuit, it's pretty easy. Because in a series circuit, there are no junctions, no splits, then in a series circuit, which means a single path, the current has to be the same everywhere. Okay, if you think of it, if there's nowhere for it to split off and go two separate ways, or three separate ways, or whatever, then it has to be the same everywhere. So the current will be equal in all points in a series circuit. That's the good thing to remember here. IT equals I1, which is equal to I2. Current is the same in all the parts of the circuit. Whereas in a parallel circuit, it's a bit different. Because there's nodes, like right here, for example, current leaves the battery as I1. It gets here to node B, or junction point B, and it splits. So I1 splits into I2 and I3. So I1 enters the node, I2 and I3 leave the node, so I can say this, that I1 equals I2 plus I3. Then when I get back up here, up to node A, they recombine because I2 and I3 are coming into the node, I1 is coming out. Remember, current in equals current out. That's the way you remember it. So I2 and I3 coming in, I2 plus I3. I1 going out must equal I1. Simple as that. That is what we call Kirchhoff's current rule. It's a rule that governs current in different types of circuits. And it applies to any type of circuit, series or parallel. Even if there's a combination, you just look at the certain points in the circuit and whether or not the current has split. But there's also a voltage rule. The voltage works a little different. What you got to remember is that electrons gain energy, gain voltage at a power source like a battery, but they lose energy in the other parts of the circuit, which we call loads. And they can be resistors, light bulbs, motors, whatever. So since we know, or we should at least have pretty good faith in the law of conservation of energy, in other words, we don't get something for nothing, then the amount of energy we lose in the circuit has to equal the amount of energy that we gained in the battery. So in other words, around any complete path in the circuit, and that's an important statement, any complete path, and you'll see why in just a second. Around any complete path in the circuit, the total voltage rises will equal the total voltage drops. Essentially, that's just conservation of energy. It means the same thing as conservation of energy, exactly. So, let's take a look at how that works. So let's look at this one. The voltage drop across R1. So we want the voltage drop right here. Okay, now in order to do that, we're going to do like a really simple circuit analysis here. So if I want to know the voltage drop, there's two ways I can do it. If I knew the voltage drop in the other two resistors, I remember that the voltage rule tells me that as I go around this circuit, they all have to add up to the total, which is 45. But I don't know the other two. So what I'm going to have to do is this. I'm first of all going to have to find the total resistance. And because this is series, all I got to do is add them up. 10 plus 15 plus 20. Remember, resistors add up in series. So that's 50 ohms. Now that I know that, I can find the total current, which is just VT over RT, which is going to be 45 over 50, or 0.9 amps. Now, Kirchhoff's current rule tells me that everywhere in that series circuit, the current is the same. So that means if IT is 0.9, so is I1. Now I can say that V1 is equal to I1 times R1. Or in other words, 0.9 times 10, which is 9 volts. Or B. Okay, so indirectly there we had to use Kirchhoff's current rule. The idea that in a series circuit, all the currents are the same everywhere. And that's what we had to do there. So we had to use a little bit of Ohm's law, a little bit of resistance, and that's exactly what you're going to do when you do circuit analysis. And we'll look at some examples of that in our next class. Anyhow, what is the voltage across the source down here? Well, remember that Kirchhoff's voltage rule tells us that the voltage increases, which is at the battery right here, has to equal the sum of the voltage drops. And there's only one path here. So what I'm going to say is this. V equals 4 plus 6 plus 2. These are all voltage drops, right? The 4, the 6, and the 2 are all voltage drops. And the V at the source, the battery, is the voltage increase. And the increases have to equal the decreases. So 4 plus 6 plus 2, 12. So 12 volts is the answer. 12.0 volts, because when you add, it's least number of decimal places, and they all had one decimal place. So you should call it 12.0. Anyway, that's it. That's all you got to do. Kirchhoff's voltage rule for a series circuit. Let's try this one. This is Kirchhoff's current rule for a parallel circuit. Remember now, we have junction points, right? So the current is going to leave the battery, and it's going to come here and split, and it's going to go here and split. So essentially what happens is it splits three ways. So the total current coming from the battery splits three ways. So I have to say it's I1 plus I2 plus I3. In other words, it's decimal 25 plus decimal 4 plus decimal 3, which is equal to decimal 95. So the total current leaving the battery must have been 0.95, because that's the sum of all the splits there. That's what the current rule tells me. It splits up, goes three different ways, and then when it gets back down to the bottom, it recombines, and those three go right back to 0.95 again. All right, let's try the next one. Next one's a little bit trickier. We have to use, again, we have to use Ohm's law. I'm going to use Ohm's law first because it tells me that total resistance is that. So I'm going to say IT is equal to VT over RT. Total current equals total voltage over total resistance. Total voltage is given as 12. Total resistance is 32, it tells me. So that's going to be 0.375 amps. That's the current flowing all the way around that circuit. So I know that the current in each one of these resistors is 0.375. Now I need to know the voltage in that resistor. Well, all I got to remember is the voltage rule tells me that around this path, all the voltages have to add up to 12. So 12 is equal to 3.8 plus 2.2 plus the missing one, which is this guy here, the V. So that tells me V equals 6 volts. So now I can find that missing resistor because R equals V over I. That's Ohm's law again. The voltage in that resistor we just found was 6. The current is the same everywhere, 0.375. Divide those two numbers, 16 is the answer. So the answer is 16 ohms. Done. That simple. Okay, so the voltage rule and the current rule is often used in conjunction with Ohm's law. And when we do circuit analysis in a little bit, you're going to see those are two of the main tools that you're going to use. Those are really the two main tools you'll use. The circuit law, or the circuit laws, the voltage and current law, and Ohm's law. Those are the ones. Plus adding up total resistance and stuff. All right, let's try the next one. What is the voltage, VT, across the source in the circuit? Well, remember the voltage law says that around any complete path. So let's draw a complete path. I'm going to draw a complete path here in red. Here's one complete path. Leave the battery, go through this resistor, and then when it gets to this junction point right here, you have to make a choice. You either go through the bottom 6 volt one or the top 6 volt. Doesn't matter. Here's one path. I can go this way, down here, back to the battery. That's one complete path. So around that complete path, I can say VT equals, I went through 8 volts. I dropped 8 volts at the first resistor and 6 volts at the second. Add those together, they equal 14. That's it. I can't go through, right, your complete path cannot go through both of those resistors with a 6 volt drop. It can only go through one or the other. That's why the answer is 14 and not 20. Yes? Remember, now, if you were going to school and you got 2 possible routes to take, you can't take the 2 of them at the same time. It's either one or the other. Okay, so you're not going to pass by both of those 6 volt ones there. All right, next one. Voltage drop across one of 3 identical resistors connected in series. Remember, when resistors are connected in series, there's one path. So the total voltage drop is going to be V plus V plus V. They're all the same, right? They're all the same voltage. So 6 is the total. It already tells us that right here. So that must be 3V, right? V plus V plus V is 3V. So I divide by 3 on both sides, and I find that V equals 2. So the answer is A, right? 2 plus 2 plus 2, 6. Because they're 3 identical series resistors. And when they're connected in series, there is only one path. All 3 of those resistors are in the path, right? If you wanted to, you could draw it. Here's your battery. There's 1 resistor. There's 2 resistors. There's 3 resistors. So as we go around that circuit, we have to go through every one of those 3 resistors because they are in series. That's what it tells us. Next question. In this one here, remember that the current coming in right here splits 3 ways. Okay, but that's only useful to me if I know all 3. So what I'm going to do now is I'm going to use this idea. I know that the current through this resistor is this. So let's find the resistance of, or let's find the voltage for that resistor. V equals I times R. Okay, so the I, 90 milliamps, divide that by 1,000 and you get 0.09 amps. You need to do that because current should always be in amps. Then I multiply that by the resistance, which is 40. That gives me 3.6 volts. 3.6 volts. Now, because these 3 resistors are all connected in series, that means they all must have the same voltage drop. Right? Because that's 3 different paths. Each path has to have the same voltage drop, so each of these 3 resistors all have to be 3.6 volts. Okay? That means they are all 3.6 volts. Right? That's what the voltage rule tells us. Any complete path, the voltage drop has to be the same. So parallel resistors will always have the same voltage drop. Always, no exceptions. What is the current through the 60 ohm? Well, I equals V over R. I know the V is 3.6. I know the R is 60. Divide those and you get 0.06 amps. Well, that's the same thing as 60 milliamps, right? Times it by 1,000. There you go. Last one on this page. We've got a 2 ohm, a 4 ohm, and a 6 ohm resistor all connected in series. If they're all connected in series, that means they all have the same current. Okay, so let's figure out what that current is. Right? Kirchhoff's current rule tells us in series they all have to have the same current. So we can find that current by doing this. First I can find the total resistance, which is 2 plus 4 plus 6, which is 12 ohms. Once I know that, I can say the current, the total current, is Vt over Rt. Okay, and Vt over Rt is going to be 24 divided by 12, which is 2 amps. So what that tells me is that everywhere in that circuit, because it's a series circuit, the current is 2 amps. So across the 2 ohm resistor, I can say V equals I times R. I now know the current is 2. I also know the resistance is 2. Multiply those together and you get 4 volts. So the answer is A. That one is done. Okay, again, there's not a whole lot to these. It gets a bit more complicated when we get into the actual circuit analysis. Okay, and when we do that in our next class, we're going to be primarily looking at Part 2 questions, because we've hardly done any of those in these last few classes. We've hardly done any of that. Okay, we've done mostly multiple choice. Because when we get into circuit analysis, that's more of a Part 2 question. Anyway, one last multiple choice before we stop. This diagram shows part of an electric circuit. This is a level 3 question. Okay, this one's a little bit trickier. We want to know the current through resistor R1. Now, there's a couple of ways to look at it. Here's a fairly systematic way to do it. I know that because these two resistors are in parallel, I can say that I know V1 equals V2. The two voltages have to be the same. V1 must equal V2. Okay, we know that because they're parallel, right? V1 equals V2. So by Ohm's law, I can say I1R1 equals I2R2. I can just substitute that. Now if I rearrange it, I can do this. I know that I1 times 15 equals I2 times 30. I'm going to divide both sides by 15. Okay, and what that tells me is I1 will be 2 times I2. In other words, whatever current's going through I1, more has to go through I2. So if I want to know the current through resistor 1, or I1, I know that when that 3 amps coming in splits, so much has to go this way, so much has to go that way. Now, which one does more go through? Well, obviously, because I1 is twice as big as I2, more goes this way, less goes this way. So if more goes that way, it can't be that answer, because if only 1 amp went that way, less would have to go the other way, and then it wouldn't add up to 3. It can't be this, so it's got to be either C or D. It can't be D, because the 3 amp splits. So if the 3 amp splits up, we can't have 3 amps going through R1. So it's got to be this. Okay? Now, there's a quick way to look at it. Just look at the two resistances, R1 and R2. R1 is only half as big as R2. That means that there will be twice as much current going through R1, because it's only half the size. Half the resistance means double the current. Okay? So that's why it's a 2-to-1 split. So 2 goes one way, 1 goes the other. The most goes through R1. That's why the answer is C. That's probably the easiest way to do that. Okay, and that brings us to the end of Kirchhoff's laws. It also brings us to the end of class number 7. Class number 8 will deal primarily with circuit analysis, but also a little bit with the cost of electricity, electrical power, those types of things. Okay, so again, study hard. Good luck with your exam.